Dzień dobry. My name is Henry Sinclair-Banks, and here is my advert for the elective course Infinite Automata. This course will run in the winter semester of the next academic year, that is 2025 to 2026. I'll be the lecturer for this year's edition of the course, and Wojciech Czerwiński will run the exercise classes. Anyway, to show you what this course has to offer, allow me to introduce an example of something we will study that I think is very interesting. So I'll quickly and informally introduce you to vector addition systems, which for ease of conversation I will call VAS. VAS are a kind of automaton that have states and transitions. Here's an example with 2 states and 4 transitions. And as the name suggests, these vectors will be labeled with vectors. In this example, the vectors are 3-dimensional and the vectors are always going to be integer vectors. A VAS also has counters that are updated by these transitions. So suppose you're in state P and you have 5 on each of the 3 counters. From this configuration, you could take the amber transition, which subtracts 1 from the first counter and adds 1 to the second counter, to get to a configuration at state P with 4 on the first counter and 6 on the second counter and 5 still on the third counter. You could then take the red transition and move over to state Q with the counter values 4, 6 and 5 remaining, and perhaps now maybe you take the blue transition and you get to a configuration with 6 on the first, 5 on the second and 5 on the third counter values respectively. An important detail, very important detail I might add, is that the counters must remain non-negative at all times. This is critical. So from this configuration Q655, you could take the blue transition up to an additional 5 times, but any more than 5 times, if you tried to take it 6 times, the second counter would take a negative value, which I forbid. This allows us to ask an already relatively interesting question, which is, from that initial configuration, so P with 5 on each of the 3 counters, can you reach the configuration which is very carefully chosen, which is state Q with counter values 640, 0 and 0? You may be able to guess that indeed by this being so carefully chosen that the answer is yes, but maybe more interestingly, how do you get there? So you start at P with 5, 5 and 5. I'm going to take this amber transition as much as I can, so 5 times, and I'll reach then a configuration with 10 on the second counter, 5 on the third, and 0 on the first counter. I'll move over to state Q, and now I'll take this blue transition 10 times. This will then put 20 on the first counter, 0 on the second, and 5 on the third. And from this point, we can't take the blue transition anymore because that would send the second counter negative. So I must take the green transition. I pop over to state Q, now with 20 on the first, 0 on the second, and 4 on the third counter. Here, I now take the amber transition 20 times, and I reach a configuration P024. I now can't take this amber transition anymore because that would send the first counter value negative. So I take the red transition over to state Q, and now I take the blue transition 20 times. I get to a configuration Q4004. And again, I'm forced to take the green transition. I reach P with values 40, 0 and 3. I then take the amber transition 40 times and end up with 0 on the first, 40 on the second, and 3 on the third counter. But by now you've probably spotted a pattern. That is that from P, you can maximally take the amber transition, then the red, then maximally take the blue transition, then the green, and end up back up with P when the second counter has doubled its value and the third counter has just been decremented by 1. So from this configuration P043, you'll be able to cycle back round to configuration P082, then P0161, and then P0320. And to finish off the run, you'll go over to state Q with 0320, and finally take this blue transition a total of 320 times to end up in the target configuration that I asked for, that was Q640, 0. Fantastic. And perhaps more interestingly, you could ask, for a given natural number n, imagine you start at the configuration Pnnn, you could ask for which natural numbers m can you reach a configuration Qm00. So you're asking which natural numbers can I reach? Like, what does this VAS, in a sense, what can it compute? I won't answer this question here. I think it's just an interesting question, and a variation of this question will be studied in the course. It's a nice exercise to get your mind jogging. Okay, I'll also touch on something that we'll talk about much later in the course, something a bit more nuanced and detailed, but I'll give you the high level idea right now. So first I'll just define the fast growing functions. You may have heard of these before. So the first fast growing function is f1, that just takes a value n and spits out n plus 1. The second fast growing function takes a value n and spits out 2n. You could view this as adding to n many times. Then the third fast growing function takes n and spits out 2 to the n. You could view this as taking 2 and multiplying itself n times. And then the fourth fast growing function is a tower of 2 to the power of 2 to the power of 2 to the power of 2. That's exponentiated n many times. And you can imagine how the remaining fast growing functions are defined from this moment onwards. And then there's the Ackermann function, which kind of collects these definitions. So the value of the Ackermann function is the nth value of the nth fast-growing function. So to give some perspective on how absurdly fast-growing this is, f1 of 1 is just 2, f2 of 2 is just 4, f3 of 3 is 2 to the 3, so that's 8, and then f4 of 4 is, well, a tower of height 4 of 2 powered with itself. So that's 2 to the 2 to the 2 to the 2. That's 2 to the 2 to the 4. That's 2 to the 16. So that's 65,536, right? And I don't even know what the fifth Ackermann value is. It's going to be an insane number. But I bring this up because something we'll show later in the course is that reachability in VAS is Ackermann complete. What does this mean? Well, the reachability problem was the problem we discussed on the previous slide. That was, you're given a VAS, an initial configuration and a target configuration, and you're just asked, in this VAS, can I go from the initial configuration somehow to the target configuration? So it's kind of like the halting problem for this automata. And Ackermann here in this theorem is referring to a complexity class. It's defined just like P time, but instead of polynomial time Turing machines, you have access to Ackermann time Turing machines. So a problem is in Ackermann if it can be computed by a Turing machine with access to Ackermann time. Insanely large class of decidable problems. And most interestingly, I claim this is complete. So not only can it be decided in Ackermann time, there is some lower bound. You need Ackermann time to decide this, which is perhaps rather surprising. And a key part of that we will definitely study in this course is that we can construct particularly involved, nasty-looking VAS that can, in a sense, compute the Ackermann functions. They start at a configuration with n on some counter, and they can reach a configuration with the nth Ackermann value on another counter and zeros everywhere else, perhaps. We'll go into more detail later, but I think this is like a surprising and fun fact to share with you. Now, I'm just going to cover the details of the main topics of this course. So early on, we'll study language emptiness for pushdown automata. Then we'll move on to problems that have undecidable reachability or halting problems. So these are two-stack, pushdown automata, and counter machines. Then we'll move on to semilinear sets and Presburger arithmetic. Then we'll move over to Parik's theorem and hopefully look at an application of Parik's theorem. We'll then study in more detail decision problems for one-dimensional vector addition systems. These are much simpler than the ones I was just talking about, and we'll look closely at various problems for one VAS. We'll also study Wall-Causey orderings and some applications, integer linear programming and some applications, and then we'll look at techniques for the decision problems called coverability and boundedness for VAS. These are similar to the reachability problem. I'll define them in the course, don't worry, but it's just to let you know this is coming up. And then, as I've already discussed, we'll be looking at fast-growing functions and Ackermann's function, and as a result, we'll be looking at the decidability of reachability in VAS, and we'll touch on some notes on the complexity of reachability in VAS. And I'll now give you one perhaps boring slide, that this course runs in the next academic year in the first semester, that's the winter semester. The lectures are in English, if you couldn't tell by now. Przepraszam, nie mówię dobrze po polsku. There will be one lecture a week. I will lecture the course. There is one formal requirement that you've taken YAO. Beyond that, there is nothing more that you need to know. This course is about a theoretical topic in computer science. There will be no programming, and as a result, there's no requirement for any programming knowledge. There'll be one exercise group that has one class per week. That class will be run by Wojciech Dziewinski, as I mentioned earlier. The exercise sheet problems will have a very wide variety of difficulties, so it doesn't really matter how confident you are at this subject, there will be something to engage you, and if you're very confident, there will be some extra starred exercises. A correct solution to these starred exercises will be worth flat credit to the module, but they won't be easy, don't worry. And perhaps what you care about most is the main assessment method for this course. That will be an oral examination, hopefully with me, at the end of the course. I will release the questions that will be asked in advance sometime towards the end of the course to give you time to prepare. I can't give you all the details right now, but the rough plan will be to have some easier questions and some harder questions. I will give you choice on what you present for the harder questions, so you can choose some proof to reproduce or some question to answer. And there will be a load of easier questions in which I'll hopefully get you to prepare as many as you can, and then I'll ask you during the oral assessment a small selection of them. Okay, I think that concludes my advert. I hope to see you next term at the Infinite Automata course. Dziękuję bardzo I zapraszam. Do widzenia.